In this experiment, I investigated the behavior of electrical current by applying Kirchhoff's laws and studying the structure and working principle of Wheatstone bridge. The main goal was to understand how current and voltage behave in a circuit, especially at nodes and closed loops. According to Kirchhoff's current law, the sum of the currents entering a node must be equal to sum of the currents leaving that node. Similarly, Kirchhoff's voltage law states that in any closed loop, the total voltage drop must be equal to zero. To practically observe these laws, I set up a Wheatstone bridge. A typical Wheatstone bridge consists of a power supply connected to 4 resistors arranged in a diamond shape. A voltmeter is placed across the middle points of the bridge to measure the voltage difference between two sides. In a balanced bridge, the ratio of the resistance on each side is equal. When this condition is met, the voltmeter shows 0 volt, meaning no current flows through the central connection. This perfectly demonstrates Kirchhoff's voltage law in practice. In this experiment, I used a multimeter, 20 volt DC power supply, 2 fixed resistors which are 100 and 150 ohms, crocodile clip cable sets, and variable resistor. As you can see, I use 100 and 150 ohm resistors, and then I set the circuit and I measure every 5 centimeter of the rheostat. After setting the circuit, I started the experiment by turning on the power supply. Then I adjusted the variable resistor by changing its length in 5 centimeter intervals, and then I recorded the voltmeter readings. Also, I specifically measured the point where the voltmeter showed the almost 0 point. After obtaining the values, I created a data table and then I create my error percentage. As you can see, the graph of the length and observed values, the length and the error percentages, and the purpose of this experiment was to introduce Kirchhoff's voltage law through a typical Wheatstone bridge circuit. During the experiment, we focused on adjusting the variable resistors to observe how electricity behaves in different conditions. Thanks to variable resistor and the application of the Kirchhoff's voltage law, we gained a clear understanding of the fundamental behavior of electrical current. As expected, from the theoretical knowledge, electricity tends to follow the path of least resistance, which was confirmed by our observations. The experiment was based on balancing the voltage differences between the parallel paths of the bridge. Ideally, the difference between the products of the voltage across the resistors in the two cross branches should match the voltage measured at the center point using a multimeter. As value of the variable resistor was changed, the voltage product in one path decreased while it increased in the other, leading the multimeter reading at the center approached 0. Although we expected multimeter to show exactly 0, in practice it displayed small negative values. These discrepancies were mainly due to experimental errors such as resistors heating up over time, which affected their resistant values. Nevertheless, despite the minor deviations, the overall trend and the sign of the measured values were consistent with the theoretical expectations.